Hello, this is Chris Rockwell and I'm presenting my work FAR. The goal of this work is to take a wide baseline image pair and predict 6 degree of freedom relative pose, meaning rotation and translation, including scale. Accurately modeling camera pose between images enables downstream tasks such as 3D reconstruction. Prior work typically takes one of two approaches: learning to directly predict pose, or detecting correspondences and using a solver to estimate the essential matrix from which pose can be recovered. These approaches have complementary strengths. Learning-based methods tend to be robust to difficult cases, but cannot produce pixel-perfect precision. In contrast, correspondence plus solver methods are highly precise in most cases, but struggle when faced with more difficult ones. This is really clear graphically. Consider this graph plotting rotation error versus rotation magnitude, which is a good measure of difficulty. We see correspondence-based methods are very accurate in easy cases, but error quickly degrades if faced with harder examples. In contrast, learning-based methods aren't as precise on easy examples, but are much more robust to higher rotation. How do we deal with these complementary attributes? FAR proposes to take strengths of both to create a precise and robust system. The idea is that classical geometry of a solver can be used to a learned system. The proposed pipeline for FAR is as follows. The learn component of FAR is a transformer which produces pose given features and correspondences. The key idea is that FAR will also have access to a classical solver producing pose from correspondences. And network output is then a learned weighting of the combination of these. This way, FAR can add solver precision to learned predictions. Through the learned weighting W, FAR learns to rely upon the transformer in difficult cases where learned methods are robust and solvers become unstable, and in easier cases to rely on the solver, which is more precise than the learned method. Now that we have a precise and robust learned output, we can use this to guide the solver. FAR uses a second pass through the solver in which it is biased by the robust learned predictions. Recall, solver output is not as robust, so this bias helps in difficult cases. This updated solver output is then combined with the transformer output to get a final result that is precise and more robust still. So let's revisit the plot from earlier. FAR is able to attain the best of both, accuracy in easy cases and robustness in difficult cases. These trends are true across 4 datasets against the state of the art. FAR can often reduce errors significantly in indoor and outdoor settings. In addition, FAR is interpretable and behaves as expected. Number of inliers correspondences is a good proxy for difficulty, and here we report error versus number of inliers. As the number of inliers decreases, the learned network is robust. While given many correspondences, the solver is precise. Correspondingly, we see little weight is given to the solver in difficult cases, while in easier cases the network almost solely relies on the solver. The result is FAR performs well in both easy and challenging cases. To summarize, FAR proposes to include a classical solver into a learned pipeline. The result is impressive accuracy and robustness. Thank you.